So this is the 8th video on rigid body kinematics. Okay, so this is in continuation of the 7th video. So before coming to 8th video, you must definitely watch the 7th video, because if you directly come to this, then you will not understand it. This has to be understood. You must first see the 7th video, then you must come to 7th video, 8th video. Okay, so I'll continue from the point where I ended in the 7th video. I'll continue from that point. Okay, so I just in 2 minutes I'll describe it, what I've done in the 7th video. This is the frame F. This is the rigid body M in plane motion with respect to F. Omega is the angular velocity of M with respect to F at the given instant. P1 and P2 are the two locations of M. R is the distance from P1 to P2. Velocity of P1 with respect to F is V1F at given instant. Velocity of P2 with respect to F is V2F at the given instant. We are given this V1F, we are given this omega, we are given this R. We have to determine V2F. If we directly use the velocity equation vector form, that becomes lengthy. Because of that determinant notation, IJK notation, omega cross R. To evaluate that determinant notation, you take time. So it was aim was to convert this entire procedure into a calculation into a scalar form. So for that I took 3 actions I took in the previous video. First action was give the velocity of P1 to P2 first. But then I said second term that if omega of M with respect to F is clockwise, then give a speed omega R to P2 at right angles to this line P1 P2 corresponding to clockwise omega. If sense of omega with respect to F is anti-clockwise, then we give a speed of omega R to P2 at normal to this line P1 P2 corresponding to anti-clockwise omega. And third action, what we have to do, we have to vectorially add the two velocities given to P2 in the first 2 steps to get the net velocity of P2. Okay, so this I just discussed in the 7th video, so that I've just summarized it. Okay, now what I'll now give a general rule for solving this class of problems. Okay, I'll give a general rule for solving such class of questions. So this is the frame F, okay, and this is the frame M, a rigid body M, which undergoes plane motion with respect to F. Goes plane motion with respect to F. Imagine that P is a location of M. P1, P2, P3, etc. They are other locations of M. Real or imaginary locations of M. P1, P2, P3, they are all in the same base plane. Points P, P1, P2 are all in the same base plane. Alright. Vector from P1 to P is vector R1, P2 to P is vector R2, P3 to P is vector R3, and so on. Alright. Now we know that from the vector formula that VPF is equal to V1F plus omega cross R1. If we write VPF in terms of V2, here V1F is the velocity of P1 with respect to F. If we write VPF in terms of V2F, it becomes V2F plus omega cross R2. If we express VPF in terms of V2F is what? Velocity of P2 with respect to F. If we express VPF in terms of P3, it becomes how much? V3F plus omega cross R3. Okay, fine. So this is all formula. Okay. If we go up till Pn, I've only shown P1, P2, P3, P4, P5, P6, other points, same base plane. Then we'll write VPF is equal to VNF plus omega cross Rn. Okay, fine. So VPF is equal to VNF plus omega cross Rn. So these are general formula. Now see, suppose we are given V1F, we know V2F, we know V3F, we know VNF, and but this we have to find VPF. So what is the first action we must do? What action we must take first? The first step we'll call it as step 1. We call it as selection. We call it as what? Selection. Step 1. We call step 1 as selection. So selection, what we'll do? will decide which point P1, P2, P3 to take, in terms of which we'll write down VPF. Okay, suppose we choose P1, that is we write VPF into using this formula. Then we say that P1 is the selected point and P is the other point. So we want to find the velocity of point P. So point P we name as other point. P name as what? Other point. We'll name P as what? We'll telling what? Other point. And P1 will be called the selected point. Suppose we want to find VPF using this equation, then we select P2. That is, if we want to find VPF using this equation, using V2F, then we find VPF. So in that case, P2 becomes the selected point. So what we'll write? Pi, arrow, here I means 1, 2, 3, and okay. We write down the name of selected point. Selected point in short we'll write as what? SP. So P is the other point and Pi is the name of selected point. Then what action we have to take? We give the velocity of P1. Suppose for the sake of argument, suppose we take P1 to be the selected point. Then we use this equation to find VPF. Then we give the velocity of V1F to VPF to P. Just as we discussed in 7th session, action 1, action 2, action 3. So step 1, we'll take action 1. We give the velocity of P1 to P. That is, we give the velocity of V1F to P. If we take P2 as a selected point, then we give the velocity of V2F to P. If we take P3 as a selected point, then we give the velocity of V3F to P. So what action we'll take? We'll give the velocity of selected point to other point. Other point in short we'll write as OP. So what is the first one? Is a selection. In selection we decide which point to be taken to be the selected point, in terms of which we have to find the velocity of other point. Alright, fine. So in step 1 selection, we write down the name of selected point, we write down the name of other point, and what action we take in step 1? We give the velocity of selected point to other point. We give the velocity of selected point to what? Other point. Fine. This is the first action. The first step we'll call as selection. Selection, why we call it selection? Because we decide we select the point other than P, using which we'll find VPF. Okay, so that is the name of selected point. Now, step 2. Step 2 is same as action 2, which we took in the 7th video. So suppose we have selected P1, we have taken P1 to the selected point. Then to find VPF, we have to evaluate this term, omega cross R1. That is same as omega R1, as we discussed in action 2 of 7th video. If we take P2 as a selected point, then we give this term to P, omega R2. Action 2 of 7th video, action 2 which I discussed in 7th video. If we take P3 as a selected point, we give omega cross R3 to P. We give omega cross R3 to what? P, as I did in the 7th video. So, step 2. So in this step, we are evaluating this term or this term or this term. Now this involves omega, angular velocity. Angular velocity applies due to rotation. So second step is the evaluation of rotation term. This term will cause as rotation. So if we take P1 to be selected point, then what action we'll take in the second step? We give a speed omega R1 to P, normal to P1, corresponding to sense of omega of m with respect to f. If you have taken P2 to be selected point, then in step 2 what action we'll take? We'll give a speed of omega R2 to P, normal to line P2P, corresponding to sense of omega of m with respect to f. If we have taken P3 to be a selected point, we give a velocity of omega r3 to P, normal to P3P, corresponding to sense of omega. If we take P4 to be the selected point, then in step 2 what action will take? We give a speed of omega r4 to P, normal to P4P, corresponding to sense of omega of m with respect to f. Okay, so in step 2 you must remember this vital statement. I'll write it here. So this you must definitely remember. Okay, OP moves in a circle. OP moves in a circle whose center is at SP. OP moves in a circle whose center is at SP. And in what action will take? Give a speed omega r dash to OP perpendicular to line joining SP and OP, corresponding to sense of omega of m, omega meaning angular velocity, with respect to f. Achha, what is r dash here? R dash is the distance between SP and OP. If you take P1 to be SP, then r dash is just r1. If you take P2 to be SP, r dash is just r2. R dash is the distance between SP and OP. So see, in step 2, this rotation term, that omega cross r term has been evaluated in much easier way. We don't have to use that determinant notation, IJK method, to calculate it. So this is time saving here. So the second step is rotation. What action will take in rotation? That also I've said it. And finally in step 3, what we have to do? We add vectorially the two velocities given to OP in the first two steps to get the net velocity of OP. That is called the combination term, because we are combining two terms vectorially. So we'll call that term as rotation, combination. The third step will be termed as combination. Third step will be termed as what? Combination. Third step will be termed as what? Combination. So in combination, what we have to do? Vectorially add the two velocities given to OP in the first two steps to get the net velocity of OP. So this I'll rub it, okay? So in this what we do, vectorially add the two velocities given to OP in first two steps to get the net velocity of OP. Okay, so third step is called combination. So this is a three-step procedure. First is selection, second is rotation, third is combination. So we call this procedure as SRC procedure for velocity. SRC procedure for velocity. SRC procedure for velocities. SRC procedure for what? Velocity. SRC procedure for velocity. S for selection, R for rotation, C for combination. In the coming videos, we will discuss, there is also an SRC procedure for acceleration also. But in this, we only take an SRC procedure for velocity. Okay, so this is called SRC procedure for velocity. S for selection, R for rotation, C for combination. Okay. Now this I'll grab it, okay. So now, what I'll do, I finally summarize this SRC procedure in a simple working rule. Working rule for SRC procedure for velocity. Working rule for SRC procedure for velocity. What action we have to working rule? What is going to be working rule? So first of all, we decide SP and OP. Okay, we decide SP and OP. So in this, we must know the velocity. One of the points should be known. We must know the velocity of SP. Otherwise, if we don't know SP, then how we find the velocity of OP? Yes, velocity of SP must be known. So we decide SP and OP. Fine. Then what do we do next? We draw the line joining SP and OP, whose orientation is same as in the question. We draw line joining SP and OP, whose orientation is same as in the question. Then what do? We give the velocity of SP to OP. We give the velocity of SP to OP. Okay. Then what do? We rewrite this sentence. This rule sentence, if you remember, then you are not going to make any mistake. OP moves in a circle. This sentence I am writing here. This, just to emphasize the importance, because this is where many students make mistake. OP moves in a circle whose center is at SP. And what action we have to take? We give a speed omega r dash to OP perpendicular to line joining SP and OP and corresponding to the sense of omega of m with respect to f. Corresponding to sense of SP and OP and corresponding to the sense of omega of m with respect to f. This is the second step, where r dash is the distance between SP and OP. R dash, which I mentioned just here, it is the distance between SP and OP. R dash is the distance between SP and what? OP. That is R dash. R dash is the distance between SP and OP. And third, what we have to do lastly, we vectorially add the two velocities given to OP to get the required velocity of OP. Vectorially add the two velocities given to OP to get its net velocity, to get the required velocity of OP. To get the required velocity of what? OP. So this is a 3-step procedure: selection, rotation, combination. So this is the working rule for SRC, procedure for velocity. First of all, we decide SP and OP, which point SP, which point OP. At least one of the points should be known, velocity should be known. Then we draw the line joining SP and OP whose orientation is same as in the given question. Then we give the velocity of SP to OP. Then we remember this sentence in mentally. OP moves in a circle whose center is at SP and radius is R dash. And what action we have to take subsequently? We give a speed omega R dash to OP, normal to line joining these 2 points, corresponding to sense of omega of m with respect to f. Action 2 as I discussed in 7th video. And then lastly, we vectorially combine the 2 velocities given to OP in the first 2 steps to get the net velocity of OP. This is the working rule for SRC procedure for velocity. Fine. This is the working rule for SRC procedure for what? Velocity. This is going to be the working rule for SRC procedure for velocity. So see one thing, when I have discussed this theory, I have assumed that the velocity of SP is known and that of OP is unknown. See, we can take the reverse also. This can happen that suppose we are given the velocity or we are not given the velocity of what I am saying is that when I have derived this, I have assumed that we know the velocity of SP, we have to know the velocity of OP. SP is given, velocity of SP is given, we have to find the velocity of OP. But sometimes if suppose velocity of SP is not given, I just write an example. Suppose velocity of P1 is known and velocity of P is unknown. Theory which I discussed here, I take this as SP and this as OP. But sometimes you can take the reverse also. But what I am saying, if velocity of P1 is known but that of P is not known, then we can take P also as the SP and we can take P1 as the OP. Okay, that also you can take. Only at least one point, velocity of one point should be known. Then only you can take other point. Okay. If P1 is also unknown, velocity of P1 is unknown and that of P is also unknown, then this method is useless. But if you know velocity of P1 and velocity of P you want to find, then you can take P1 as SP, P1 as SP and P as OP. Or you can take P1 as OP and P as SP. But one point should be known, that's all. And then other velocity of other point can be evaluated. But velocity of one point should be known, that's all. That's the important point. Okay, velocity of one point should be known. So if velocity of P1 is known, P is unknown, velocity of P is unknown, then we can take P1 to be SP and P to be OP. Or we can take opposite also. We can take P to be the SP and P1 to be OP. Okay, so this is the 8th video on rigid body kinematics. I fully discussed it. Okay, so 9th video on rigid body kinematics, I'll take up numerical problems. Okay, so the 7th and 8th video, they are very important of chapters of rigid body kinematics. They should be known completely. Okay, so in 9th session on rigid body kinematics, I'll take up numericals based on this velocity equation. Fine, so I close it here.